Welcome. Take a moment to settle in. Without trying to find the perfect position, turn the volume down to the point where my voice is only just audible, a little below what would be comfortable in daylight. Nothing that follows needs to be remembered, or understood, or followed to the end. You can fall asleep at any point, and you will not miss a thing. Tonight we are going to talk about the moon, slowly, without hurrying. Of all the objects visible without instruments, the moon is the only one that shows a face. Everything else in the night sky is a point of light or a soft patch of haze, but the moon presents a disk about half a degree wide, easily covered by the tip of an outstretched finger, and across that disk lie markings that do not change from one generation to the next. Those markings, and the steady rhythm by which the lit portion of the disk grows and shrinks, gave every culture that watched the sky a set of facts to work with, long before anyone thought of pointing a lens upward. The cycle begins, by most reckonings, with the thin crescent that appears low in the western sky shortly after sunset, curved like a bow, with its opening turned away from the horizon. Each evening after that, the crescent thickens and stands higher, until about a week in it has become a half disk, lit on the side facing the sun, and cut down the middle by a straight edge. The lit portion continues to swell through the shape called gibbous, rounded on both sides but not yet complete, and roughly 14 or 15 days after the first sighting the disk is whole, rising in the east as the sun sets in the west. Then the sequence runs backward, the light retreating from the western edge until the last worn crescent rises just before dawn and is lost in the brightening sky. From one new moon to the next, that whole cycle takes about 29.5 days, which is why nearly every early calendar settled on months of 29 or 30 days. The phases themselves arise from nothing more complicated than the angle at which the sun's light strikes the moon relative to the direction from which we watch. Half the lunar globe is always in daylight and half in darkness, and what changes is how much of the daylit half happens to be turned toward Earth. The boundary between the two, the line the sunrise or sunset is crossing on the lunar surface, sweeps slowly across the disk over the course of the month. That geometry also fixes when the moon can be seen. A crescent is close to the sun in the sky, and therefore keeps company with it, rising and setting within a few hours of it, while a full moon sits opposite the sun and is above the horizon for most of the night. Between those extremes, the half-moon trails or leads the sun by roughly a quarter of a day, which puts the waxing half-disk high in the sky at sunset and leaves the waning half-disk hanging in the blue of the morning. The moon in daylight is a common sight rather than an oddity, pale against the sky and easy to overlook, and half the time it is above the horizon, it shares that horizon with the Sunday. Night by night, the moon also shifts eastward against the background of stars by something like 13 degrees each day, which is more than 20 times its own width. An observer who notes which stars it passes will find that it returns to the same place among them in a little over 27 days, rather shorter than the interval between one full moon and the next. The difference comes from the sun's own apparent motion along the sky during the same period. By the time the moon has completed a circuit of the stars, the sun has moved on, and the moon needs another 2 days or so of travel to catch up with the same lighting angle. One consequence, familiar to anyone who watches regularly, is that moonrise falls later each day by roughly 50 minutes. Across all of this, the pattern on the disk holds still. The same arrangement of dark and pale regions faces Earth at every phase, at every season, from every country. And it faced the same way for the people who described it thousands of years ago. Since the moon travels around the Earth, keeping one hemisphere turned toward us requires that it turn once on its own axis in exactly the time it takes to complete one orbit. And it does. The synchrony is not coincidence, but the outcome of tidal forces working over a long stretch of time, gradually breaking whatever faster spin the young moon had until rotation and revolution locked together. The lock is not perfect, and a patient eye can catch the slack in it. Because the lunar orbit is not a circle, the moon runs a little ahead of or behind its average pace at different points, and because its axis is slightly tilted with respect to the orbit, it nods gently north and south. The combined effect is a slow rocking, a few degrees each way, that carries features near the edge of the disk into view, and then hides them again. Over many months, this exposes about 59% of the lunar surface to Earth-based observers, though never more than half at any single moment. Near the beginning and end of each cycle, when only a narrow crescent is lit, the rest of the disk is often faintly visible as well, filled with a soft grey glow that lets the whole round outline be traced. Country observers in the English-speaking world called this the old moon in the new moon's arms. The glow is sunlight that struck the Earth first, reflected from oceans and cloud tops, crossed the intervening space, and lit the lunar night before returning to us. Seen from the moon, the Earth at those moments hangs nearly full, close to 4 times as wide as the moon appears from here and considerably more reflective, so the lunar night is never entirely dark. The explanation is generally credited to Leonardo da Vinci, who worked it out in his notebooks well before any telescope existed. The markings themselves divide plainly into 2 kinds. Large stretches of the disk are grey and comparatively smooth, with rounded outlines, and they are concentrated toward the middle and the northern portion of the visible hemisphere. The rest is lighter, and looks mottled and uneven, even without magnification. The paler ground reflects close to twice as much sunlight as the grey plains, which is enough contrast for the unaided eye to separate perhaps a dozen distinct dark regions and to remember their arrangement. Those greyer areas are floods of basaltic lava that welled up and cooled long ago, filling the floors of enormous basins. The brighter terrain is older, higher, and far more heavily pitted. What people made of the pattern varied with where they stood and what they knew. Across much of Europe, the arrangement was read as a face, or a full figure, a man carrying a bundle of sticks, sometimes with a dog. In China, the same shapes were seen as a hare, standing at a mortar and pounding the ingredients of an elixir, and the hare, or rabbit, appears again in Japanese, Korean, and Indian tellings, and independently in Mesoamerica, where the rabbit in the moon is old and widespread. Elsewhere, the markings suggested a woman, a toad, a crab, a set of hands. The differences are a matter of which patches are grouped together and which are treated as background, and the persistence of any one reading within a culture says something about how carefully and how often the disk was looked at. Color and apparent size come mostly from the air between the observer and the moon rather than from the moon itself. Low on the horizon, the disk is reddened and dimmed, for the same reason and by the same mechanism that reddens the setting sun. And it often looks strikingly large there, although any measurement shows it to be no wider than when overhead. Thin, high cloud made of ice crystals will surround it with a ring of light at a fixed angular distance, a halo that many traditions took as a sign of coming weather, and that does, loosely, indicate approaching cloud. The moon's real distance varies enough over the month to change its width by a little more than a tenth, though that change is spread over 2 weeks and passes unnoticed. Brightness, on the other hand, rises far more steeply than the lit fraction alone would suggest. A full moon is close to 10 times as bright as a half moon, partly because at that moment the shadows cast by every stone and ridge on the surface fall directly behind them and out of sight. Full moonlight casts shadows on the ground, dims the fainter stars, and gives enough illumination to walk unfamiliar country without stumbling, which mattered a great deal to travelers, herders and armies for as long as the night belonged to the sky rather than to lamps. Counting long stretches of time by the sun alone is awkward work, since one day is much like another, and the year turns too slowly to be felt from week to week, while the moon offers a unit of middling size that anyone can verify by looking up, a shape that changes nightly, repeats itself in a little under 30 days, and requires no instrument, no written record, and no official to confirm it. That unit, the month, is the oldest division of time that human communities took directly from the sky and held on to. Certain notched bones from the late Paleolithic have been read as tallies of lunar phases, though the reading is disputed and probably beyond settling. And by the time writing appears in Mesopotamia, the lunar month is already the working frame of the civil year. Babylonian practice tied the month to a single observable event, the first appearance of the thin crescent low in the west after sunset, which meant that the day began at nightfall, and the month began with a sighting reported by watchers on a clear evening. Because the interval from one new crescent to the next averages a little more than 29.5 days, and varies by several hours around that average, months came out with either 29 or 30 days in an order that could not be predicted by any simple rule, and scribes recorded which kind had just ended. Over centuries, these records accumulated into continuous observational diaries, which later served purposes their compilers never had in mind. Adjustment to the seasons was the harder problem, since 12 of these months fall about 11 days short of the year of the sun, and a purely lunar count of 12 slips backwards through spring, winter, autumn, and summer in roughly a third of a human lifetime. Mesopotamian administration solved it at first by decree, inserting a 13th month whenever the barley was plainly late or the equinox had drifted too far from the month that was supposed to contain it, the extra month being given the name of the one it followed. By the 5th century before the Common Era, the insertions had settled into a fixed pattern of 7 additional months in every 19 years, applied without waiting on a judgment about the crops. Egypt took a different road and largely abandoned the moon for civil purposes. The administrative calendar there ran to 365 days without exception, 12 months of 30 days each plus 5 days added at the end, and since no quarter day was ever made up, the whole scheme slid backwards against the seasons by 1 day in 4 years, and returned to its starting point only after some 14 centuries. That steady slippage made the calendar useless for predicting the Nile flood, but excellent for arithmetic, because any 2 dates could be subtracted without correction, which is why Greek astronomers later adopted it for their own computations. Alongside it, the temples kept a separate lunar reckoning for ritual service, so the two systems ran in parallel for a very long time. Chinese calendrical practice kept both the moon and the sun, and refined the joint system over many dynasties. Months began at the conjunction of moon and sun rather than at the first sighting of the crescent, once calculation became good enough to fix that moment, and the solar year was divided into 24 terms, marking the progression of the seasons. The rule that emerged placed an intercalary month, wherever a lunation happened, to contain none of the principal solar terms, which produces 7 extra months in 19 years without anyone having to count them out in advance. Issuing the calendar was an imperial function, prepared by an office of astronomers, and a change of dynasty was often marked by a reformed calendar so that the accuracy of the lunar tables carried political weight as well as agricultural use. Across the Greek world, the same problem was handled far less tidily, since each city kept its own month names, its own festival year, and its own magistrates, with the authority to insert or omit days as convenience required. Months alternated between 29 and 30 days in principle, and in practice the civil count could wander several days away from the actual phase, which sailors and farmers simply ignored in favor of the sky itself. An Athenian comedy of the late 5th century has the moon complain that the days are not being kept in their proper order, a joke that only works if the audience knew perfectly well that the official calendar and the visible moon had parted company. Meton of Athens is the name attached to the 19-year cycle in the Greek tradition, from work in the same period, and the arithmetic behind it is straightforward. 235 lunations come to very nearly 19 solar years, the two counts differing by only a couple of hours, so a scheme of 12 ordinary years and 7 years of 13 months brings moon and sun back into step for generations before the small residue matters. Babylonian astronomers had been applying an equivalent rule already, and the Greek achievement lay in stating it as a numbered cycle of days that could be tabulated. Callippus later dropped a single day from 4 such cycles to improve the fit, and the geared instrument recovered from a wreck off Antikythera carries a spiral dial divided into 235 parts, showing that the cycle had passed from the astronomers into mechanism. Hebrew reckoning kept the month firmly lunar, while insisting that Passover fall in the spring, which forces the year to be lunisolar, and made the intercalated month a matter of religious necessity rather than administrative tidiness. A second month of Adar was added before the spring festival when the season demanded it, and the decision rested with the court, taking account of the ripeness of the barley, the state of the roads and the readiness of the pilgrims, as well as the position of the Sunday. Determination of the new month depended on witnesses who had seen the crescent and came to testify, after which the news was carried outward, first by signal fires on the hilltops and later by messengers, a slower method that left distant communities uncertain for a day and gave rise to the practice of keeping 2 days for certain festivals. Witness testimony gradually gave way to calculation, and the rules of the fixed Jewish calendar took shape over several centuries in late antiquity and the early medieval period, arriving at a 19-year cycle with 7 leap years, months of settled length with 2 that vary, and a set of postponements that prevent particular holy days from falling on inconvenient weekdays. The result is a calendar that can be computed indefinitely in either direction from arithmetic alone, in which the first of each month still falls close to the true conjunction, usually within a day, even though nobody is required to go outside and look. Arabia before Islam used a lunar year with an inserted month by an arrangement whose details are imperfectly known, and the practice of intercalation was prohibited in the Quran, leaving a calendar of 12 lunar months and nothing else. That decision has a clear consequence. The Islamic year runs about 354 days, so its months move backwards through the solar seasons by roughly 11 days annually and complete a full circuit in about 33 years. Ramadan therefore falls in the long hot days of summer for some years and in the short cold days of winter for others, and a person of ordinary lifespan will keep the fast in every season. Because the beginning of each month was to be marked by the sighting of the crescent, a considerable body of astronomical work grew up around the question of when a young moon becomes visible at all, a matter that depends on its angular distance from the sun, the angle at which its path meets the horizon, the clarity of the air, and the sharpness of the observer's eye. Astronomers in the Islamic world produced visibility criteria and tables, while jurists debated whether a sighting in one place established the month for another, and both discussions continue in modified form today. A tabular version, running 11 longer years in every 30, was also devised for administrative convenience, and it tracks the true moon closely without ever waiting on the weather. Christian communities inherited the problem in another guise. Since Easter is fixed by a lunar rule anchored to the spring equinox, and the tables built to compute it in the early medieval West leaned on the same 19-year cycle, each year of the cycle receiving a number that a computist could look up. Roman civil timekeeping, meanwhile, had already cut its months loose from the sky, and the reformed calendar of the late Republic gave them lengths that suit the solar year and match no lunation at all, although the word for month in Latin and in its descendants, as in the Germanic languages, still carries the moon inside it. What every one of these systems shares is a reliance on a signal that no authority could counterfeit and no one had to be taught to read, available to a shepherd and a scribe on equal terms, marking out intervals long enough to organize a market, a debt or a pilgrimage, and short enough to hold in memory without writing. The friction between that signal and the slower turning of the seasons was never resolved so much as managed, month by inserted month, and the arrangements each society settled on tell a good deal about what it valued: exact agreement with the sky, or arithmetic that never needed correction, or a fast that visits every part of the year in turn. An eclipse interrupts the pattern that the phases establish, and it does so without any warning an unaided observer could gather beforehand, since the moon rises full and unremarkable, and then, over the better part of an hour, slides into a dimness that has an edge to it, a curved edge creeping across the disk from one side and leaving behind not blackness but a dull coppery red, which is sunlight bent through the whole ring of Earth's atmosphere and spilled into the shadow. Eclipses of the sun are rarer at any given spot and stranger in their effects, because the dark cone the moon casts on Earth is narrow, sweeping a track only 100 or so kilometers wide, so that a village may lie in complete darkness at midday, while a neighboring valley sees only a bite taken out of the solar disk. Averaged over the long run, a particular town waits some 3 or 4 centuries between total solar eclipses, while the moon slips at least partly into Earth's shadow once or twice in most years, visible at that moment from the entire night side of the planet. In the cuneiform record of Mesopotamia, These events were read as messages rather than mechanisms, and the great compilation of celestial omens gathered on tablets over centuries assigned meanings to eclipses according to the month, the watch of the night, the direction from which the darkening began, and the quarter of the disk first touched. Scribes attached to the Assyrian court wrote to the king with their observations and their interpretations, and the letters that survive show a professional class arguing about cloud cover, about whether an expected eclipse had in fact occurred, and about what the omen required. When the sign was taken to threaten the king's life, a ritual existed to divert it. Another man was installed on the throne for a period, given the trappings of office and the danger that went with them, while the true king withdrew and was addressed by another title until the danger was judged to have passed. Chinese court records treat eclipses with comparable seriousness and considerably greater administrative regularity, and inscriptions on oracle bones from the Shang period note the darkening of the sun and the moon among the events worth recording. Later dynastic histories preserved eclipse notices as part of the state's business, since the ruler's mandate was bound to the orderly behavior of the heavens, and a failure of the light called for ritual response, drumming and offerings, and the correction of whatever fault had provoked it. The value of these archives outlived the beliefs that produced them, because a bureaucracy that writes down the date of every darkening for 2,000 years leaves behind a dataset no individual lifetime could assemble. Because the same archival habit prevailed in Babylon, the scribes there eventually noticed something that no single observer could have found, which is that eclipses repeat. Counting the months between one eclipse and a later one, very like it, they arrived at an interval of 223 lunations, a little over 18 years and 11 days, after which the moon returns to nearly the same phase, the same distance, and the same position relative to the crossing points of its tilted orbit. A tablet listing eclipse possibilities at that spacing lets a scribe say, well in advance, which months of which years are dangerous, and the late Babylonian material includes such lists, along with the beginnings of a method for predicting the timing and magnitude, rather than merely the occurrence. Halley, in the 17th century, gave that interval the name Saros, borrowing a Babylonian word whose original sense was different, and the name has stuck. The period is not a whole number of days, exceeding 6,585 by about a third. So the next eclipse in a series occurs 8 hours later in the day than the last, and Earth has turned roughly a third of the way round beneath it, carrying the track of a solar eclipse about 120 degrees west in longitude. 3 Saroses together, some 54 years and a month, restore the whole day count and bring the shadow back to something near the same part of the world, which is why an observer with a long enough family memory might see the pattern locally, while a scribe with tablets could see it from anywhere. Anaxagoras, in the 5th century before the Common Era, is credited with stating the physical cause plainly. The moon shines by light received from the sun, and it grows dark when Earth comes between the two and blocks that light. He held the moon to be of earthy stuff, with level ground and depressions in it, and he explained solar eclipses as the moon passing in front. The idea may have had precursors among earlier thinkers whose works survive only in fragments, and the biographical tradition of antiquity reports that Anaxagoras was prosecuted at Athens for impiety, which suggests that removing divinity from the sky was not received as a neutral proposal. Whatever the details, the explanation had a property the omen tradition lacked. It made predictions about shape and geometry that could be checked. Aristotle drew one of those checks in his treatise on the heavens, pointing out that the boundary of Earth's shadow on the moon is curved in every eclipse, whatever the season, and whatever the moon's height above the horizon, and that only a sphere casts a shadow curved from every direction. This was offered alongside other arguments, but it is the cleanest of them, and it rests on nothing more than watching carefully and noticing that the edge never comes out straight. Aristarchus of Samos took the geometry further in a short work that has come down to us, reasoning that when the moon appears exactly half lit, the angle at the moon between the directions to Sun and Earth must be a right angle, so that measuring the angle at Earth between Sun and Moon at that instant fixes the shape of the triangle, and therefore the ratio of the two distances. He took the angle as 87 degrees, and concluded that the Sun lies between 18 and 20 times farther away than the Moon. The logic is sound, and the measurement is beyond what the eye can do, since the true angle is closer to 89 degrees and 50 minutes, and the real ratio is near 400, and the moment of exact half illumination is itself hard to judge. From the same work follows the conclusion that the Sun is much the larger body, a result that Archimedes says led Aristarchus to propose that Earth moves around it. Width of shadow supplied the other half of the argument. During a lunar eclipse, the observer can compare the size of the dark region the moon is crossing with the size of the moon itself, and Aristarchus took Earth's shadow at that distance to be about twice the lunar diameter, the modern figure being nearer 2.5. Combining that comparison with the fact that the Sun and Moon appear almost exactly the same size in the sky, one can work back to the Moon's diameter as a fraction of Earth's, and the classical results came out in the right region, giving a body roughly a quarter to a third the width of Earth. Hipparchus, working in the 2nd century before the Common Era with better instruments and access to the Babylonian eclipse records, refined the distance considerably. An account preserved by later commentators describes him using a solar eclipse that was total at the Hellespont and about 4/5 obscured at Alexandria. The difference between the two views arising from the moon's parallax, its apparent shift against the sky when seen from two places. He also used the observed breadth of Earth's shadow at the moon during lunar eclipses, and the figures attributed to him fall in the neighborhood of 60 to 70 Earth radii, straddling the true mean of a little over 60. Ptolemy, 3 centuries later, settled on 59. Converting those ratios into a measured length required knowing the size of Earth, which Eratosthenes had estimated from the difference in the Sun's noon altitude between 2 Egyptian cities, and the chain from there to the moon is complete in principle even if every link carries an error. Eclipses served one more practical purpose in the same period. Since a lunar eclipse begins at the same physical moment everywhere it can be seen, so that two observers comparing the local time they recorded were measuring the difference in their longitudes, a use Hipparchus is said to have recommended, and that geographers pursued for centuries afterwards. Timings written down in Babylon and Athens and Alexandria are still consulted, because comparing where those eclipses were actually seen with where the equations of motion say they should have been seen gives a measure of how much Earth's rotation has slowed in the intervening 2,500 years. A device made by Dutch spectacle grinders, described to the States General in the autumn of 1608, spread across Europe within months, and by the following summer versions of it, could be bought in Paris and London from craftsmen who had reasoned out the arrangement of lenses for themselves. Thomas Harriot, a mathematician attached to the household of the Earl of Northumberland, obtained one of about 6 times magnification and pointed it at the moon in late July of 1609, sketching a crescent with a division between light and dark that ran not as a clean arc, but as a broken, indented line, and marking a few patches whose identity is hard to recover from so rough a drawing. He wrote nothing for publication. His papers passed to heirs and then to archives, so that the first known telescopic record of another world sat unread while the news came from elsewhere. Galileo Galilei, teaching at Padua, learned of the instrument, ground his own lenses, and by the end of that year had built glasses reaching roughly 20 times, good enough that the boundary between lunar day and night resolved into something with structure. Through the autumn and winter, he made repeated observations, recording them in ink and wash, and in March of 1610, he published a short book in Latin, the Sidereus Nuncius, in which the lunar plates appeared alongside his account of Jupiter's attendant bodies and the resolution of the Milky Way into separate stars. His central observation about the moon was not a picture, but an argument from shadow. Specks of light appeared in the darkness ahead of the terminator, grew, and eventually joined the illuminated portion, exactly as sunrise touches a mountain summit before it reaches the plain below. From the length of those shadows and the geometry of the lit hemisphere, Galileo worked out an estimate for the height of some lunar peaks, arriving at figures above 4 miles, greater than any elevation then credited to Earth's own ranges. The conclusion he drew and stated flatly was that the moon is not smooth and polished, as the schools had taught of the heavenly bodies, but rough and uneven, marked with hollows and swellings much like the terrain underfoot. That single sentence carried more weight than the drawings, because the physics of Aristotle assigned corruption and irregularity to the sublunary world alone. A body with mountains and pits was a place, subject to landscape, and by extension the boundary between the terrestrial and the celestial had lost one of its supports. Harriot, reading the Sidereus Nuncius in England, went back to the moon with better glasses and over the following 2 years produced something Galileo never attempted, a map of the whole visible disk assembled from observations at different phases, with features numbered and their positions fixed as well as his instruments allowed. He shared it with a small circle of correspondents and left it at that. His reticence has been explained in various ways, none of them certain, and the effect was that his charts entered the record only when scholars examined his manuscripts centuries afterwards. Priority, in this case, mattered less than circulation, since the questions the telescope raised were settled by people arguing over printed plates rather than private ones. Bright ground and dark ground, once seen sharply, invited the most natural reading available in the 17th century, that the pale regions were land and the dark ones water. Johannes Kepler, responding to Galileo's book within weeks, took the analogy seriously, treating the dark expanses as seas and the bright as continents, and in his posthumously printed lunar fiction he went further, remarking on the regularity of the round hollows and entertaining the thought that they were excavations made by inhabitants seeking shelter from the long day. Galileo himself grew doubtful. In his dialogue of 1632, he had his spokesman argue that a broad sheet of water, being smooth, would behave as a mirror and throw back the sun from a single small area while appearing dark elsewhere, whereas rough land scatters light in every direction and looks uniformly bright, so the dark plains were more likely to be flat, dull terrain than any ocean. Michael van Langren, cosmographer to the Spanish court in Brussels, printed a named chart of the moon in 1645, the first to reach publication with a full scheme of labels attached. His interest was practical as much as descriptive, since the slow advance of sunlight across identifiable lunar peaks offered a clock visible from any ship or shore, and a navigator who could recognize the moment a particular summit caught the sun would in principle know the absolute time and therefore his longitude. To make that work, he needed features with agreed names, and he supplied them from the world he depended on, honoring kings, nobles, saints, and patrons. Almost none of his choices survived, though his own name remains on a crater near the eastern limb. 2 years afterwards, in Danzig, the brewer and municipal officer Johannes Hevelius brought out the Selenographia, a folio he had observed, drawn, and engraved himself, and which set a standard for detail that held for well over a century. He recorded the moon phase by phase, described the small rocking motions that let an observer see somewhat more than half the globe over time, and gave the features terrestrial names, transplanting the Apennines, the Alps, the Caucasus, and the Carpathians onto the lunar landscape, along with Etna, Sinai, and a scatter of islands and straits. His system was learned and consistent, and it had the disadvantage of confusion, since a reader met the same geography twice over. What endured from it were the mountain chains, which keep their borrowed names to this day. Bologna produced the rival scheme in 1651, when the Jesuit Giovanni Battista Riccioli published his Almagestum Novum, a compendium of astronomy containing a lunar chart drawn by his colleague Francesco Maria Grimaldi. Riccioli divided the visible disk into 8 sectors and distributed the names by a logic of his own, assigning the craters to astronomers, mathematicians, and philosophers, ancient and modern, and giving the dark plains a vocabulary of weather and mood: sea of tranquility, sea of serenity, sea of crises, sea of showers, ocean of storms, marsh of decay, lake of dreams. The words are his, and they carry the old water reading in their grammar, even where he was careful about the physics. Riccioli did not accept the motion of the Earth, holding to a compromise system. Yet, he placed Copernicus, Kepler, and Aristarchus on the chart in the ocean of storms, and noted in his text that he had set the Copernicans afloat. Both schemes circulated together for decades, and the Bolognese one won, partly because the Almagestum Novum was consulted as a reference across Catholic and Protestant Europe alike, and partly because a list of scholars can be extended indefinitely as new features come into view, whereas the supply of familiar earthly ranges runs out. Later, cartographers added their own contemporaries in the same manner, so that the near side accumulated a rough chronology of science written in crater names, and disputes about who deserved a place ran on among astronomers for generations. Formal control came only in the 20th century, when an international committee sifted the accumulated usage, discarded duplicates, and confirmed a standard set, keeping Riccioli's planes and much of his role of philosophers. Doubt about the water accumulated gradually rather than arriving in one stroke. Observers watching year after year saw no tides along the supposed shores, no clouds passing over the bright regions, no seasonal change in the outline of anything, and shadows within the dark plains that fell as crisply as those on the highlands, which is not how a fluid surface behaves. Occultations told the same story from another direction, since a star passing behind the limb of the moon vanished abruptly instead of dimming and shifting as it would through an atmosphere, and without air there could be no standing open water. By the 18th century, most working astronomers had let the oceans go, while the names stayed exactly where Riccioli had put them, which is how a plain in the northeastern quadrant of the near side, dry for something like 3,000 million years, came to be called a sea of tranquility. Kepler reached toward the right explanation while pursuing a different problem entirely. In the preface to his book on the motion of Mars, published in 1609, he set down the idea that the waters of the sea are drawn upward by the body of the moon, and that if the Earth ceased to hold its oceans down, they would rise to meet it. He had no way to turn that intuition into a quantity, and his notion of the force that kept planets moving was closer to a sweeping push carried round by the rotating sun than to a pull along the line joining two bodies. Galileo, who thought tides arose from the combined spin and orbital motion of the Earth shaking the ocean basins, dismissed the lunar explanation as a relic of astrology. The idea persisted anyway, unproved and unquantified, for most of a century. A young astronomer in Lancashire took the next step in the 1630s. Jeremiah Horrocks, working largely alone and dead before he was 25, applied Kepler's ellipse to the moon rather than to the planets, placing the Earth at one focus and allowing two things that no earlier scheme had allowed together. The long axis of the ellipse could swing back and forth about its mean position, and the eccentricity could grow and shrink in step with that swing. This single device absorbed the largest of the irregularities that had troubled lunar tables since antiquity, and it did so with a geometry that could be drawn. His manuscripts, circulated after his death, were printed decades later and were used at Greenwich by the first astronomer royal. Newton adopted the same construction and refined its constants, so that the most accurate lunar model of the 17th century descended from a man who never lived to see it published. Woolsthorpe, in the plague years of 1665 and 1666, is where Newton, recalling the period in old age to acquaintances who wrote it down, placed his first comparison between the falling of an apple and the holding of the moon. The comparison is arithmetical rather than poetic. Should the pull of the Earth weaken as the square of the distance from its center, then at the moon's distance of about 60 Earth radii, it must be weaker by a factor of 3600, and the moon, in each second, ought to fall away from a straight line. By that fraction of the distance, a stone falls at the ground. The moon does fall, continuously, and only its sideways motion keeps the fall from ever reaching the surface. When Newton set the figures against each other, he found agreement close enough to be encouraging, though the size of the Earth he used at the time was imperfect, and the full demonstration waited until the Principia appeared in 1687. Universal gravitation made the moon a harder object rather than an easier one. Under the attraction of the Earth alone, it would trace a fixed ellipse forever. But the sun pulls on it as well, and pulls unequally on the moon and on the Earth. So the elliptical path is continually stretched, tilted, and swung around. Newton showed that this single extra force accounted for the inequality that Tycho Brahe had detected in the 16th century for the steady backward slide of the points where the lunar path crosses the plane of the Earth's orbit, a circuit completed in a little over 18.5 years, and for the forward creep of the long axis of the orbit, which comes round in a little under 9 years. The last of these was the trouble. His analysis yielded roughly half the observed rate, and he never publicly resolved the shortfall. For 60 years, the discrepancy sat in the literature as the strongest evidence against the inverse square law. Around 1747, Alexis Clairaut, having attacked the problem alongside D'Alembert and Euler, proposed adding a small term varying as the inverse fourth power of distance, which would be undetectable at planetary distances and sufficient at lunar ones. Within 2 years, he withdrew the suggestion, carrying his approximations one stage further into terms he had earlier judged too small to matter. He found that the neglected quantities contributed almost as much as the ones he had kept, and the calculated motion of the orbit's long axis rose to meet the observed value. Euler and D'Alembert confirmed the result independently. The lesson was about the treachery of successive approximation rather than about gravity, and it left the law standing unamended. Tides received their first quantitative treatment in the same work that established the law. Newton reasoned that the moon pulls the near side of the Earth more strongly than the center, and the center more strongly than the far side. So the ocean is drawn into a slight elongation with a rise on both sides, which is why most coasts see 2 high waters a day rather than 1. The sun produces a smaller elongation of its own, and when the two act along the same line, the range grows, while at the quarters they partly cancel. This equilibrium picture explains the fortnightly rhythm and fails at almost every particular harbor, where the actual times and heights depend on the shape of the basin. Laplace supplied the missing framework late in the 18th century by treating the ocean as a thin layer of fluid on a spinning globe, responding to a periodic driving force as any oscillating system responds, with delays and amplitudes set by depth and geometry. Halley's contribution came from patience with records rather than from analysis. Comparing the timings of eclipses reported by ancient observers with the positions that contemporary tables gave for those dates, he concluded in the 1690s that the moon's mean motion was very slowly increasing. Appointed to Greenwich in 1720, already past 60, he set himself to observe the moon through a complete cycle of about 18 years, the interval after which the geometry of eclipses repeats, on the reasonable ground that a full circuit of observations would expose every periodic error in the tables at once. He lived to finish it. The accumulated data fed directly into the practical problem that had motivated the effort, which was the determination of longitude at sea. Longitude is a difference of time, and a navigator who knows the hour at a reference meridian and the hour aboard ship can convert the gap into distance east or west. Lacking a clock that could keep the reference hour through months of damp and pitching, mariners could use the sky itself, and the moon is the only body that moves fast enough against the stars to serve as the hand of such a clock, crossing its own width in roughly an hour. Measuring the angle between the moon and the sun, or a bright star, then comparing it with a table predicting that angle for successive hours at Greenwich, yields the reference time. The method needs lunar predictions accurate to about 1 minute of arc, since an error of that size becomes half a degree of longitude, and no table of the 17th century came close. Tobias Mayer, at Göttingen, brought them within reach around 1755 using observations of his own, together with an analytical treatment supplied by Euler, whose successive lunar theories developed the technique of letting the constants of an ellipse vary slowly with time instead of holding them fixed. Trials at sea, including those conducted by Neville Maskelyne, showed Mayer's tables holding to something near the required accuracy. The British Board of Longitude, established by the Act of 1714, awarded £3,000 to Mayer's widow after his early death, and £300 to Euler for the underlying analysis, and from 1767, the Nautical Almanac published the lunar distances in a form a ship's officer could use with a sextant and a few hours of arithmetic. Laplace gathered the whole subject into the volumes of his Celestial Mechanics at the close of the century, and turned back to the acceleration Halley had inferred. He traced it to the slow decrease in the eccentricity of the Earth's orbit under the influence of the other planets, which alters the Sun's average disturbing effect on the Moon and quickens its motion, and his computed rate matched the historical eclipses well enough to close the question for 2 generations. John Couch Adams reopened it in the 1850s by showing that a more careful expansion gave only about half the observed amount. The remainder was eventually assigned not to gravitation among the planets, but to friction in the tides themselves, slowly lengthening the day and altering the standard against which the Moon's motion had been measured all along. Johann Hieronymus Schröter, chief magistrate of the small town of Lilienthal near Bremen, spent the closing decades of the 18th century turning a private observatory toward a surface that most astronomers of his day regarded as already sufficiently known. He worked by shadows, timing how far a peak threw its darkness across the plane below and converting that length, with the sun's height deduced from the position of the terminator, into an elevation above the surrounding ground. His 2 volumes of selenotopographical fragments, the first appearing in 1791 and the second in 1802, gave European readers the fullest description of the lunar surface, then in print, and gave them the word rill for the narrow winding clefts he traced on the floors of the plains, a term that has survived every later revision of the vocabulary. Schröter also believed he saw the surface alter from month to month, and reported changes of tint and outline that later observers could not confirm, which left his reputation divided between the diligence of his record and the looseness of his inferences. French troops plundered and burned the Lilienthal establishment in 1813 during the campaigns in northern Germany, destroying instruments and a portion of his unpublished material, and he died a few years afterwards without having brought the work to any settled conclusion. What he left behind was less a map than a demonstration that the Moon rewarded systematic attention, and that the labor of describing it would take a lifetime rather than a season. In Dresden, a land surveyor named Wilhelm Gotthelf Lohmann took up the task with the habits of his profession, which meant fixing points before drawing lines between them. He planned a chart of the visible hemisphere in 25 sections, each built on measured positions rather than on the eye's estimate of where a feature ought to sit, and he issued 4 of those sections in 1824. Failing eyesight stopped him before the rest could be engraved, and the completed work waited more than half a century for publication, by which time the surveying principle behind it had become the ordinary standard of the field. 2 men in Berlin carried that principle to its first full realization. Wilhelm Beer, a banker with a private observatory and a small refractor, and Johann Heinrich Madler, The astronomer who used it began a coordinated survey in the late 1820s, dividing the disk into quadrants and returning to each region under many angles of sunlight so that a feature, invisible near full moon, could be caught when the shadows were long. Their map appeared in 4 sheets between 1834 and 1836, close to a meter across when joined, and the accompanying volume of 1837 listed measured positions for a great many points and heights, for well over 1,000 elevations. For the origin of their coordinate system, they chose a small bright crater near the center of the disk, Mosting A, whose position they determined with particular care and which served as the fundamental reference for lunar mapping long afterwards. Their conclusions were as consequential as their measurements. Beer and Madler compared their own drawings with everything reliable that had come before, found no alteration they could defend, and stated that the moon showed neither water nor an appreciable atmosphere nor any sign of ongoing change. Coming from the most exacting survey yet made, that verdict had the effect of closing a subject rather than opening one, and for a generation the visible hemisphere was widely treated as a finished chart, of interest chiefly to those correcting details at its margins. Johann Friedrich Julius Schmidt was not persuaded that the details were finished. Trained in Germany and appointed to the observatory at Athens, where the sky was steadier than in the north, he drew the moon for some 40 years, incorporating Lohrmann's unpublished sections into his own work and pressing the scale far beyond anything attempted before. His chart of the lunar mountains, published in Berlin in 1878 in 25 sections and approaching 2 meters in diameter when assembled, recorded craters by the tens of thousands, along with rills, ridges, and the low terraces that step down the inner walls of the larger ring plains. The drawing alone represented a quantity of hand labor that no subsequent map would ever repeat, because by the time anyone might have wished to, the plate had taken the work over. Schmidt was also responsible for the episode that unsettled the doctrine of a changeless surface. In 1866, he announced that the crater Linné, a well-defined pit on the plain of Mare Serenitatis, recorded by Lohrmann and by Beer and Madler, no longer appeared as a crater at all, but as a whitish patch with only a slight depression at its center. The report set off 2 decades of dispute, drew observers of every degree of experience to that one spot on the plain, and never produced agreement, since the older drawings had been made with different apertures under different illumination by men who had no reason to suspect their sketches would one day be used as legal evidence. In Britain, William Radcliffe Burt organized a committee under the British Association intended to settle such questions by systematic re-observation and a common register of features. Though the effort outran the volunteers available to it and ended without completing its survey, the remedy for disagreement between 2 draftsmen was a record that neither had drawn. John William Draper, in New York, made a daguerreotype of the moon in 1840 with an exposure running to some minutes, obtaining an image on which the larger dark planes could be distinguished. A little over a decade later, working with the 15-inch refractor at Harvard, John Adams Whipple and the observatory's directors produced daguerreotypes good enough to be exhibited at the Great Exhibition in London, where they were received as a novelty of some scientific promise rather than as a working instrument. Warren de la Rue, in England, brought the wet collodion process to the problem in the 1850s, using a reflector of his own construction and a clock drive accurate enough to hold the image steady while the plate was exposed. He noticed that the moon's libration, rocking the same hemisphere slightly toward and away from Earth over the course of weeks, presented the surface from two marginally different directions, so that photographs taken at opposite phases of that rocking could be viewed together as a stereoscopic pair, the relief standing out as it does to two eyes. Lewis Morris Rutherford, in New York, attacked the optical side of the difficulty, since a lens corrected to bring visible light to a sharp focus does not do the same for the blue and violet rays to which early emulsions were most sensitive, and he had an objective figured specifically for the chemically active part of the spectrum, obtaining lunar negatives in the 1860s that stood comparison with the best drawings. What limited the plate was not the emulsion, but the air above the telescope. Turbulence in the Earth's atmosphere smears fine detail on any exposure long enough to register the fainter parts of the surface, while the trained eye can seize the instance of steadiness between one shudder and the next, and for several decades skilled visual observers could genuinely record features that no photograph then showed. The plate's advantage lay elsewhere. It fixed the whole illuminated hemisphere in one moment, without selection or memory, and it could be measured afterwards under a micrometer by someone who had never looked through the telescope at all. At the Paris Observatory, Maurice Loewy and Pierre Puzeau used the Coude Equatorial to build a photographic atlas issued in installments from 1896 into the following decade, choosing illuminations deliberately so that each region appeared with the shadows that best revealed its structure, and adding descriptive text that argued about the origin of what the plates showed. Around the same period, Samuel Arthur Saunder measured photographic negatives to derive positions for a network of control points across the disk, giving selenography the geodetic framework that hand-drawn charts had only approximated. The question of a lunar atmosphere was settled by a different sort of observation. When the moon passes in front of a star, the star vanishes at the limb instantly, without the gradual dimming, color change or displacement that even a thin envelope of gas would impose by refraction, and repeated timings of such occultations push the permitted density lower with each improvement in technique. Supporting evidence accumulated from the sharpness of the terminator, the absence of any twilight arc beyond it, the failure of clouds or haze ever to obscure a feature, and the lack of any bending of sunlight around the limb during solar eclipses. Toward the end of the century, the kinetic theory of gases supplied a reason rather than merely a limit, since molecules at the temperatures of the lunar day move fast enough that a body with so weak a surface gravity cannot retain them for long. A surface without air is a surface without wind, rain, or running water, and therefore one on which whatever made the craters had left its work essentially undisturbed. Two explanations were available for the ringed pits that cover the lunar surface, and both had been proposed within a lifetime of the first telescopic drawings. Robert Hooke, in the book of microscope observations he published in 1665, tried each of them with his hands. He dropped bullets into a soft paste of clay and water and obtained small circular hollows with raised rims and, in some cases, a rebound mound at the center. He also heated powdered alabaster mixed with water until bubbles rose and burst, leaving rings on the setting surface. The second experiment persuaded him more, not because it fitted the appearances better, but because he could think of no plausible supply of bodies falling out of the sky, the idea of stones traveling between the planets being at that time without standing among natural philosophers. That reservation held for well over a century, and it shaped what followed. Volcanoes were known. They built circular structures with central vents, and terrestrial geology offered them ready to hand as a model, so the ring plains of the moon were read as craters in the ordinary sense of the word. Schroeter described them in those terms. Later observers refined the description, and by the 1870s the volcanic account had reached its most developed form in the work of James Nasmyth and James Carpenter, who built plaster models of lunar landscapes, photographed them under raking light, and published the results alongside a theory in which molten material welled up, spilled outward in a ring, and left a cavity whose floor sank below the surrounding plain as the interior withdrew. Objections to the rival account were substantial and honestly stated. Bodies arriving from space would strike at every angle, and a slanting blow ought to gouge an elongated scar. Yet the lunar rings are close to circular almost without exception, from the smallest that could then be resolved up to the largest walled plains. Central peaks look like vents. The floors of the great rings lie lower than the country outside them, which is awkward for a pile of thrown-out debris and natural for a collapsed reservoir. And nowhere on the moon could anyone point to the buried remains of the objects that were supposed to have done the work. Advocates of collision persisted nonetheless. Franz von Paula-Gruthuysen argued in the 1820s that falling bodies had made the formations, and later in the century Richard Proctor pressed a meteoric hypothesis in England, noting that the rings run in a continuous series of sizes with no preferred diameter, whereas terrestrial vents cluster within a narrow range, and that the bright streaks radiating from certain young formations behave like material thrown out along straight paths, rather than like anything a volcano produces. Their case rested on appearances and analogy, and it lacked the physics that would have answered the objection about circularity, so it remained a minority position. Grove Carl Gilbert brought the methods of field geology to the question. Chief geologist of the United States Geological Survey, and a man accustomed to reading landforms for their history, he spent part of the winter of 1892 at the Naval Observatory in Washington with its large refractor, and published his conclusions the following year under the title The Moon's Face. He repeated the impact experiments with clay balls, and more importantly, he mapped what he called the sculpture around Mare Imbrium, a system of grooves and ridges radiating from that basin across hundreds of kilometers of older terrain, gouged, he argued, by material flung outward at low angles from a single enormous collision. Superposition told him which features came first. The pattern told him where the energy had come from. Gilbert's reasoning failed him on the one terrestrial case he examined at first hand. Visiting the circular hole in the Arizona desert, now known as Meteor Crater, he weighed two hypotheses, tested for a large buried iron mass with magnetic instruments, found none, compared the volume of the rim with the volume of the cavity, and found them equal, and concluded that a subterranean steam explosion offered the better account. Daniel Barringer took the opposite view from 1903 onward and drilled for years in search of the iron he expected to lie beneath the floor. The mass was never located, and the reason emerged only much later, once the energies involved were calculated properly. An object arriving at tens of kilometers per second carries far more energy than is needed to melt and vaporize itself, and most of it does not survive the encounter. That same calculation dissolved the circularity objection. In the 1920s, the New Zealand physicist Algernon Charles Gifford set out the argument in print. At cosmic speeds, the incoming body is stopped within a distance comparable to its own diameter. Its kinetic energy is released almost at a point just below the surface, and the resulting excavation is driven by that release rather than by the direction of travel. An explosion makes a round hole whatever direction the fuse came from. Central peaks became a rebound of deep material rather than a vent. Raised rims became overturned strata and fallback, and the depth of the floor ceased to be an embarrassment. Ralph Baldwin assembled the quantitative case in 1949 in The Face of the Moon, a book written outside the professional astronomical community and, for a time, largely outside its notice. Having seen bomb craters and their measurements, he plotted the depth of craters against their diameter for terrestrial explosion pits, for the Arizona structure, and for lunar formations across the whole observed range, and found that all of them lay along one continuous relationship, while volcanic cones and calderas fell elsewhere on the same diagram. He also proposed that the dark Maria were impact basins, whose floors had later been flooded by lava rising from within, which reconciled the two schools by giving each its own domain. Argument nonetheless continued through the 1950s, and it turned partly on the interior of the Moon rather than on its surface. Harold Urey held that the body was cold and largely undifferentiated, a survivor from the earliest stage of the solar system, while Gerard Kuiper argued for substantial melting and for volcanic activity on a serious scale. Neither man doubted that some collisions had occurred. What divided them was the proportion. Meanwhile, the genuinely volcanic features of the Moon were being catalogued as well: the sinuous rills, the low domes with summit pits, and the dark deposits that mantle certain regions. So the volcanic tradition retained real ground even as it lost the craters. Eugene Shoemaker settled the terrestrial half of the problem by finding a physical signature. Working at Meteor Crater and comparing it with craters produced by nuclear tests in Nevada, where the sequence of overturned beds could be studied in a structure of known origin, he and Edward Chow identified coesite in the Arizona rocks in 1960, a dense form of silica that forms only under pressures no volcano generates. And shortly afterwards, they recognized the same mineral in the Ries Basin in southern Germany, a broad depression that had been mapped for decades as a volcanic feature. Shock metamorphism thus became a test that could be applied in the field and in thin section. Confirmation came in from several directions at once. Surveys of the Canadian Shield, undertaken from the Dominion Observatory in Ottawa, added circular structures whose deformed rocks and gravity signatures matched the new criteria. Shatter cones, the fractured fans that Robert Dietz argued were diagnostic of shock, turned up at site after site, and the catalogue of recognized terrestrial impact structures grew from a handful to dozens. Meteoritics, which had begun to establish itself as a science only after the fall at Leyig in 1803, was investigated and accepted, now supplied both the projectiles and the rates at which they arrive. By the time spacecraft returned close photographs, the outcome was no longer seriously in doubt, and the images confirmed it in detail. Craters at every scale, down to the smallest the cameras could resolve, chains and clusters of secondary pits arranged radially around the larger ones, and continuous blankets of ejected debris draping the terrain outside their rims. The rocks brought back completed the picture, since the highland samples proved to be breccious, fragments broken, mixed, shocked, and welded together repeatedly, containing feldspar converted to glass by pressure, while the mare samples were basalts erupted long after the basins that hold them had been carved out. Rocket vehicles able to leave Earth altogether appeared within about a dozen years of the end of the Second World War, and with them came a chance to settle by direct approach a set of questions that observation from below had left standing. Nobody had seen the hemisphere permanently turned away. Nobody knew whether the surface would hold a weight, or whether the fine material that covered it lay a few centimeters deep or several meters. The smallest features, resolvable through the atmosphere, were still a kilometer or two across, which meant that a landing site could be judged smooth on the best available photographs and still be strewn with boulders and pits large enough to tip a spacecraft over. Machines sent to look closely would answer all three questions within a decade, and would do so in an order dictated as much by the reliability of launch vehicles as by any plan. Soviet attempts began first. In January of 1959, a probe later designated Luna 1 passed the Moon at a distance of several thousand kilometers, missing the intended impact, but becoming the first object built by people to escape Earth's gravity and take up an orbit around the Sun. Its magnetometer found no appreciable lunar magnetic field, and its instruments registered the stream of charged particles flowing outward from the Sunday. That September, a second craft did strike, coming down on the near side and ending transmission at the moment of contact, which was itself the confirmation that it had arrived. Both flights were short, both carried a modest instrument load, and both established that the trajectory calculations were sound to within a margin that would soon be tightened. Luna 3, launched in October of the same year, carried something more ambitious: a camera loaded with film, a small chemical laboratory to develop and fix and dry that film aboard the spacecraft, and a scanner to convert the dried negatives into a signal that could be sent home. Passing beyond the Moon and looking back at the sunlit far hemisphere, it exposed its frames, processed them over the following hours, and transmitted from a distance where the signal was weak and the noise considerable. The pictures that emerged were coarse, streaked, and difficult to interpret, and they were enough. The hidden hemisphere proved to be crowded with craters, and largely without the broad dark plains that dominate the face we see, a difference nobody had predicted and which would take decades to explain. Two features were clear enough to name, and the Soviet astronomers gave one dark patch the name Mare Moscoviense and attached the name of Tsiolkovsky to a conspicuous crater with a bright central peak on a dark floor. American efforts through the same period ran into a long sequence of launch failures and spacecraft that fell silent. The Ranger series was designed to fly a deliberately fatal course, transmitting television pictures continuously until the moment the vehicle struck, and the early members of that series either missed, or arrived without power, or carried cameras that never switched on. Success came in the summer of 1964, when Ranger 7 descended into a mare region south of Copernicus and returned pictures at steadily increasing magnification for the last quarter of an hour of its existence. The plane it hit was afterwards called Mare Cognitum. Two more followed within 8 months, one into Mare Tranquillitatis and one into the crater Alphonsus, the last of them broadcast live as it fell. Between them, the three sent back something on the order of 17,000 frames, the final ones resolving objects well under a meter across, and what those frames showed was that cratering continues without a lower limit. Every smooth-looking surface, examined closely, dissolved into overlapping shallow depressions down to the resolution of the lens. Whether such a surface would support a lander remained unresolved. Thomas Gold had argued that fine particles, ground down by micrometeorite bombardment and moved about by electrostatic charging, might accumulate in the low basins to a considerable depth and behave like a powder into which a solid object would simply sink. Radar echoes from Earth suggested a porous but reasonably firm upper layer, and thermal measurements during eclipses pointed the same way. Yet an inference drawn from radio waves was not the same as a footpad resting on the ground. Contact came in February of 1966. Luna 9 approached with retro rockets firing, ejected a cushioned capsule shortly before impact, and let it bounce to rest in Oceanus Procellarum, where 4 petals folded back to right it, and a small rotating camera began to sweep the horizon. The facsimile transmission was picked up in Britain by the radio telescope at Jodrell Bank, and because the format was recognized, the pictures appeared in the British press before the official Soviet release. What they showed was a surface of firm consistency, close textured, littered with stones, a few centimeters across, and pitted by shallow hollows, with the near ground sharply defined and a slightly raised horizon a short distance away. The dust question was effectively closed. 2 months afterwards, Luna 10 became the first object to orbit the Moon, and its gamma-ray measurements indicated that the surface materials resembled basalt rather than the granitic rocks common in Earth's continents. The American soft landers arrived that June, with Surveyor 1 setting down in the same broad plane and returning more than 11,000 pictures over its first lunar day, including views of its own footpads, which had pressed only a few centimeters into the ground. 6 more were launched over the following 19 months, and 5 reached the surface intact. One carried a scoop on an extending arm and dug trenches, pushed at rocks and measured the force required, finding a material that held vertical trench walls and clumped when compressed, cohesive rather than free-flowing. Others carried an alpha scattering instrument that bombarded the soil with particles from a radioactive source and read the energies of what came back, yielding the first direct chemical analysis performed on another world. The Mare samples proved rich in oxygen, silicon, aluminium, calcium, and iron in proportions close to terrestrial basalt. The last of the series came down in the rough, bright terrain north of the crater Tycho, well outside the equatorial band where landings were expected, and its analysis returned more aluminium and less iron, the first quantitative sign that the highlands and the plains are made of different rock. One of the landers restarted its engines after arrival and hopped a few meters sideways, both to test how the surface responded to rocket exhaust and to give stereoscopic views of ground it had already photographed. Photographic coverage adequate for choosing where to land came from 5 orbiters flown between the summers of 1966 and 1967. Each carried a film camera with 2 lenses of different focal length, a processing system that developed the negatives against a moving web of chemically treated tape, and a scanner that read the developed film line by line and sent it down in strips to be reassembled on the ground. The first 3 concentrated on candidate sites within a narrow equatorial belt, photographing them at sun angles that brought out slopes and small obstacles. The 4th worked from a high polar orbit and mapped nearly the whole near side systematically. The 5th filled in the far side and returned targeted views of specific features. Taken together, they covered almost the entire Moon, at resolutions that in places distinguished objects a meter across. and among the frames was a view of Earth taken from lunar orbit, a crescent above a foreground of cratered ground. Tracking of these craft revealed something unexpected in itself. The radio signal showed slight accelerations as they passed over the circular Maria, and the analysis published in 1968 attributed them to concentrations of mass beneath those basins, a lumpiness in the interior that had to be included in any trajectory calculation. Each orbiter, when its film was exhausted, was commanded to strike the surface so that its transmitter would not confuse later missions. Circumlunar flights without landing continued in parallel, and in the autumn of 1968, a Soviet craft looped around the Moon carrying biological specimens, photographed the surface on the way past, and was recovered on Earth, demonstrating that the return trajectory and the heat of atmospheric entry at that speed could both be survived. By then, the accumulated evidence described a surface of known bearing strength, known slope statistics, known thermal behavior, and known composition in outline, photographed closely enough that a landing ellipse could be drawn on a map and defended. 6 Apollo landings between July of 1969 and December of 1972 brought back something on the order of 380 kilograms of lunar material, collected as loose soil scooped into bags, as individual rocks lifted with tongs, as short tubes driven into the regolith with a hammer, and, on the last 3 flights, as cores drilled nearly 3 meters down with a battery-powered rotary percussive tool. Each sample was photographed where it lay before being picked up, so that its orientation and its setting could be reconstructed afterwards, and the containers into which the bags were sealed, closed on knife-edge indium seals, meant to hold the lunar vacuum during the journey home. In Houston, the boxes went into a purpose-built laboratory, where the material was opened inside cabinets flooded with dry nitrogen, weighed, catalogued, split, and distributed to investigators who had been chosen and equipped years in advance. Soviet engineers took a different route to the same end, sending 3 automatic craft that landed, drilled, and launched a small capsule straight back to Earth without any human aboard. Luna 16, in September of 1970, returned about 100 grams from Mare Fecunditatis. Luna 20, early in 1972, drilled into highland ground near the crater Apollonius. Luna 24, in the summer of 1976, recovered a long, slender core from Mare Crisium, weighing something under 200 grams. Their combined yield came to roughly 300 grams, 1,000th of what the crewed flights carried, but it came from places no astronaut visited, and small quantities were exchanged between the 2 programs, so that laboratories on both sides could measure material from sites their own missions had not reached. Unpacked and examined, the first Tranquility rocks proved to be basalt, dark and fine-grained, with rounded cavities left by gas that had come out of solution as the lava cooled, and with a mineral assemblage that any terrestrial petrologist would have recognized in outline: pyroxene, calcium-rich plagioclase, olivine in some specimens, and an abundance of the titanium iron oxide ilmenite that was higher than in almost any lava flow on Earth. That single observation settled a question that had stood since the 17th century, since basalt forms only from molten rock, and the dark plains were therefore floods of lava rather than dust bowls, sediment beds, or dried seas. Subsequent landings sampled other maria and found basalts of differing composition. some rich in titanium and some poor in it, some carrying more aluminium, all of them the products of melting deep inside the moon and eruption onto its surface. Pale fragments scattered through the same soil pointed in another direction entirely. They were anorthosite, a rock made almost wholly of calcium-rich plagioclase feldspar, light in color and low in density, and their presence in a mere landing site meant that they had been thrown there from the brighter uplands. When later missions landed in and near the highlands, anorthosite and rocks related to it dominated the collection, which gave the bright terrain a composition as well as a name. Feldspar of that kind is buoyant in basaltic melt, and the interpretation that took hold within a year of the first return was that the outer few hundred kilometers of the young moon had been molten, and that plagioclase crystallizing in that melt had risen to form a crust, while denser crystals of pyroxene and olivine settled downward. Dating the material was the work of laboratories in several countries, using rubidium and strontium, potassium and argon, uranium and lead, and later samarium and neodymium, each pair a clock running at its own rate, and each providing a check on the others. Mare basalts came out mostly between 3,000 and 4,000 million years old, with the sampled flows spanning several hundred million years of eruption. Highland rocks ran older, reaching back toward 4,500 million years, close to the age of the solar system itself as measured in meteorites. On Earth, plate motion, erosion, and burial have destroyed or reworked nearly everything from that period, leaving a handful of much altered outcrops and some tiny surviving crystals, so the lunar collection provided a record of the first 600 million years of planetary history that no terrestrial quarry could match. An unforeseen consequence followed from putting absolute ages on rocks whose landing sites had been photographed from orbit. Counting craters per unit area had long given a relative sequence, since a surface accumulates impacts in proportion to how long it has been exposed, but the counts could not be converted into years without a calibration point. Sampling several surfaces of different crater density and dating each one supplied that calibration, and the resulting curve, steep in early times and much flatter thereafter, was then applied to unsampled parts of the moon and, with assumptions about impact rates, extended to Mercury, Mars, and the satellites of the outer planets. Much of the chronology used across the inner solar system still rests on those few dated landing sites. Highland samples were rarely simple. Most were breccias, aggregates of older fragments welded together by the heat and pressure of impacts, some of them containing breccias within breccias, recording several generations of shattering and reassembly. Radiometric dating of the melted portions produced a cluster of ages near 3,900 million years, and one reading of that clustering was a burst of heavy bombardment at that time, an idea argued over ever since, partly because the landing sites were few and lay close together, and partly because ejecta from a single enormous basin might have showered all of them at once with material of one age. Dryness turned out to be a defining property of the whole collection. Terrestrial rocks nearly always contain minerals with water bound into their crystal structure, amphiboles, micas, clays, and none of these appeared in the lunar samples. The iron in them was so little oxidized that grains of metallic iron sat unaltered among the silicates, and the samples showed no rust when eventually exposed to laboratory air, unless they had been contaminated. Elements that vaporize easily, sodium among them, were depleted relative to Earth, Decades afterwards, instruments capable of measuring parts per million found small quantities of water and other volatiles trapped inside beads of volcanic glass from the same collection, which modified the picture without overturning it. The Moon is dry by comparison with Earth, though not absolutely so. No trace of life was found, and none of the more careful searches for organic compounds turned up anything above the level of contamination introduced by the spacecraft, the tools, and the laboratory itself. The possibility had been taken seriously enough that the earliest crews, their spacecraft, and their cargo were held in quarantine on return in a sealed facility where the samples were also exposed to plants, insects, fish, and mice to see whether anything sickened. Nothing did. The biological testing program closed without a positive result, and quarantine was dropped after the third landing. Between the rocks lay the soil itself, a grey powder produced by billions of years of impacts grinding the surface, containing angular mineral fragments, beads of glass formed in those impacts, and agglutinates, which are grains of soil fused together by tiny strikes into welded clumps. Solar wind particles had been driven into the outer skin of every exposed grain, so the soil carried hydrogen, helium, neon and argon of solar origin, and a foil sheet unrolled facing the sun on several missions and brought home for analysis gave a direct measurement of the noble gases the sun emits. Instruments were left behind on each landing to work long after the crews departed, powered by generators that produced electricity from the heat of decaying plutonium and commanded from Earth through their own transmitters. Seismometers at 4 sites operated as a network for years, recording deep quakes that recurred with the tides, shallower ones, thermal cracking at dawn, and the impacts of meteoroids and of discarded rocket stages deliberately steered into the ground. Magnetometers, heat flow probes sunk into drilled holes, detectors of the thin gas above the surface, and arrays of corner cube reflectors for laser ranging joined them. The seismic network was switched off in the autumn of 1977 for want of funding, having shown a layered interior with a crust tens of kilometers thick, and having shown too that the dry fractured rock rings for an hour or more after a shock instead of damping it away. Long before any of that material reached a laboratory bench, the question of where the Moon had come from was a problem in mechanics as much as in geology, because the pair has properties that are awkward to arrange by chance. Measured against its planet, the Moon is large, about a quarter of Earth's diameter, a ratio matched nowhere else among the rocky worlds. Its mean density, close to 3 1/3 grams per cubic centimeter, falls well below Earth's 5.5, which means it carries proportionally far less iron. And the spin of Earth, together with the Moon's orbital motion, adds up to a quantity of angular momentum that any account of the system's formation has to supply from somewhere and then conserve, since nothing can remove it once it is there. George Darwin, working in the late 1870s on the mathematics of tidal friction, took the recession of the Moon and ran it backwards in time. The calculation brought the Moon steadily nearer to Earth and shortened the terrestrial day until, at the far end, the two bodies were nearly in contact, and the day lasted only a few hours. From that, he proposed that the Moon had separated from a molten, rapidly spinning Earth, perhaps helped by a resonance between the planet's oscillations and the solar tide, leaving behind a body of mantle material in orbit. The idea was taken up widely, and one geologist suggested that the scar left by the departure was the basin of the Pacific, a proposal that survived until the ocean floors were dated and found to be young. Fission had a difficulty that would not go away. To throw material off its equator, a fluid Earth needs to be turning far faster than the present system can account for, and there is no mechanism to carry away the surplus angular momentum afterwards. Detailed treatments of the process, once they became possible, showed that a body shedding mass in this way tends to produce a filament rather than a satellite, and that the shed material falls back or disperses. Capture offered a different route. On this account, the Moon formed elsewhere in the solar system, in a region where iron was scarcer or where the mixture of elements differed, and was later caught by Earth during a close approach. Harold Urey, whose chemical work on the early solar system carried great weight in the years before the landings, inclined towards something of this kind, holding that the Moon might be a primitive object preserved almost unaltered from the beginning. The mechanics were the trouble. A body arriving from interplanetary space passes by unless a great deal of energy is dissipated in the few hours of the encounter, and no plausible sink for that energy could be found, while the near-circular orbit and its modest inclination to Earth's path around the Sun looked nothing like the elongated, randomly tilted orbit that a capture would leave behind. The third family of ideas asked for no special event at all. If Earth grew by sweeping up smaller bodies, then some of that debris might have gone into orbit rather than onto the surface, accumulating into a companion that formed alongside its planet from the same reservoir at the same time. Co-accretion explained the orderly orbit without strain, and it fitted comfortably with the general picture of planet building. What it could not explain was why the two bodies differ so much in iron content, having drawn on one supply, nor why the system holds so much angular momentum, nor why the Moon should be so depleted in the elements that evaporate easily. By the middle of the 1960s, then, each of the three accounts had been examined closely enough to reveal a contradiction with something measured, and none commanded general assent. Much of the scientific case for sample return rested on the expectation that rock in hand would decide the matter, or at least narrow it. What came back described a body that had been thoroughly melted early in its history. The highland crust of calcium-rich feldspar pointed to an ocean of magma hundreds of kilometers deep, from which light minerals had floated and heavy ones sunk, which ruled out the cold primitive relic the capture had been invoked to preserve. Bulk composition confirmed the iron shortage that density had implied, with only a small metallic core at the center. The rocks were strikingly poor in elements that boil away at moderate temperatures, sodium, potassium, and lead among them, and correspondingly enriched in the refractory ones, and they contained no minerals bearing water in their structure, no clays and no micas, nothing that forms in the presence of a fluid. Alongside those chemical results came a measurement of a subtler kind. Oxygen occurs as 3 stable isotopes, and the proportions among them vary from one part of the solar system to another in ways that survive melting and mixing, so that each class of meteorite plots on its own line when the ratios are graphed against each other. Lunar samples, analyzed at Chicago and afterwards at other laboratories with steadily finer precision, fell on the same line as terrestrial rocks, with no separation that the instruments could detect. The material of the Moon had formed at essentially the same distance from the Sun as the material of Earth, out of the same regional stock. A proposal that accommodated all of this appeared in the middle of the 1970s, put forward independently by 2 pairs of researchers, one arguing from the cratering record and the size distribution of early bodies, the other from calculations of orbital dynamics. Late in the assembly of the planets, they suggested, an object roughly the size of Mars struck the growing Earth a glancing blow. The metal core of the striking body sank inward and merged with Earth's own, while silicate matter from the outer parts of both was flung outward, some of it escaping, some falling back, and some settling into a disk that accreted into a single satellite in a span perhaps as short as years or centuries. The blow itself would deliver the angular momentum of the system in one stroke. The orbiting material would be mantle rather than metal, and the heat involved accounts for both the magma ocean and the loss of the volatile elements. Debate ran on for a decade before the idea was widely adopted, and a conference held at Kona in Hawaii in 1984 is generally taken as the turning point, since the older explanations were set beside the impact model there and came off worse. Computing power arriving over the following years allowed the collision to be simulated directly, with the colliding bodies represented as clouds of particles carrying mass, energy, and momentum, and those calculations mapped out which combinations of impactor size, speed, and angle of approach could yield a satellite of the right mass in an orbit of the right size. The impacting body was later given the name Theia, after the figure who in Greek myth was mother of the moon goddess. Success brought its own complication. Most simulations placed the majority of the disk material, often 3/4 of it or more, in matter that had belonged to the impactor rather than to Earth, and a body assembled elsewhere would be expected to differ isotopically. Yet no difference could be found. Through the 1990s and the 2000s, the comparison was extended to titanium, chromium, silicon, and tungsten, and each element told the same story of near identity. 3 kinds of response have been developed. That the impactor grew in Earth's own orbital neighborhood and shared its composition from the start, that the disk and the molten planet exchanged material freely through a common atmosphere of rock vapor until they equilibrated, and that the collision was more violent than first supposed, mixing the 2 bodies thoroughly and leaving a surplus of spin that a later resonance with the solar tide could carry away. Dating the event has been attempted through the decay of one short-lived isotope of hafnium into tungsten, which registers the moment a core separates from a mantle, and through lead isotopes in the oldest crustal rocks. Results differ by tens of millions of years depending on the chronometer and the assumptions, but they agree in placing the formation of the Moon within roughly the first 100 million years of the solar system, while Earth was still finishing its own assembly. The collision, on this reckoning, is part of Earth's history as much as the Moon's, a stage of planetary growth whose record was long ago erased at home by melting, weathering, and the slow turning over of the crust, and preserved instead in the dry rock of a companion that never had the means to destroy it. The Moon's axis stands almost upright with respect to its path around the Sun, tilted by roughly 1.5 degrees, and that near vertical posture has a consequence at the poles that the Earth, leaning by more than 23 degrees, never experiences. Sunlight at the lunar poles arrives grazing the horizon at all times of year, so the floors of deep craters near 90 degrees of latitude are never touched by it, not in the course of a lunar day, not in the course of a year, not in the course of 1 billion years. Scientists working in the early 1960s reasoned that such places would act as cold traps, holding any volatile molecule that wandered in and settled, and that hydrogen compounds delivered over long ages by comets, meteorites, and the solar wind might accumulate there rather than escaping to space, as they do everywhere else on that airless world. Testing the idea required spacecraft in polar orbit, and the first came in the mid-1990s when Clementine transmitted radio signals into shadowed southern craters and listened for the echo with antennas on Earth. The return showed a change in polarization of the kind that ice can produce, though rough rocky ground can produce something similar, and the result was argued over rather than accepted. Lunar Prospector followed at the end of the decade with a neutron spectrometer, an instrument that detects hydrogen indirectly by measuring how cosmic ray neutrons lose energy in collisions with light nuclei near the surface. Both poles showed a deficit of fast neutrons in exactly the regions where permanent shadow lay, which indicated hydrogen in the upper meter or so of soil, without specifying whether that hydrogen was locked in water, in hydroxyl, or simply implanted as bare protons from the solar wind. Direct sampling arrived in 2009. A spent rocket stage was aimed into Cabeus, a crater near the lunar south pole, and struck at several kilometers per second, while a small trailing spacecraft flew through the debris cloud with spectrometers running before it too hit the ground. Watched from orbit and from telescopes on Earth, the plume contained water vapor and water ice, along with other volatiles such as carbon monoxide, ammonia, and methane, in proportions suggesting that the regolith at that spot held something of the order of 5% water by mass. The same year brought an American imaging spectrometer aboard India's first lunar orbiter, which found a spectral signature of water and hydroxyl, not only at the poles, but across wide swathes of the surface, strongest in the cold of morning and weakening as the ground warmed, implying molecules being made, moved, and remade by the solar wind striking silicate soil. Since then, the Lunar Reconnaissance Orbiter has mapped the polar terrain in fine detail with a laser altimeter, measured surface temperatures with an infrared radiometer, and imaged shadowed ground by ultraviolet starlight and by light scattered from nearby illuminated slopes. The radiometer found floors where the temperature stays below about 30 Kelvin, cold enough to hold not only water but nitrogen and carbon compounds indefinitely. What remains unsettled is the form the ice takes. Some deposits appear as thin frost mixed through the loose soil at concentrations of a few percent. Some patches look like coherent sheets, and much of the polar hydrogen may sit buried beneath a dry protective layer, stirred and scattered over billions of years by small impacts that turn the surface over grain by grain. Interest in these deposits runs in two directions at once. Water at the poles would be a resource for any long stay, since it can be split into breathable oxygen and rocket propellant without hauling mass out of Earth's gravity, and much of the current program of landers and rovers is directed at the polar regions for that reason. The scientific value is different, and in some ways greater, because a cold trap that has never warmed holds a stratified record of what has arrived at the inner solar system across geological time, comet by comet and asteroid by asteroid, in the order of arrival, undisturbed by the chemistry and weather that erase such records at home. The second modern line of inquiry needs no spacecraft in orbit at all, only the equipment left standing on the surface. Apollo 11, 14, and 15 each deployed a panel of corner cube reflectors, prisms cut so that light entering from any reasonable angle returns along the path it came. and 2 French-made arrays of the same kind rode to the Moon on the Soviet Lunokhod rovers. Observatories fire short laser pulses at these targets and time the round trip, which lasts about 2.5 seconds. The beam spreads to a few kilometers wide by the time it reaches the Moon, and spreads again on the way back, so that of the enormous number of photons in each pulse, a single one may return, or none at all, and a useful measurement is built from thousands of shots. The first results in 1969 were good to a few tens of centimeters, and half a century of refinement has brought the distance between a station on Earth and a reflector on the Moon to a precision of millimeters. Accumulated over decades, those measurements give a number that had been suspected since the 18th century but never pinned down. The Moon is moving away from the Earth at approximately 3.8 centimeters per year. The mechanism lies in the tides. Earth's oceans are pulled into bulges by lunar gravity, but the planet rotates beneath them faster than the Moon travels along its orbit, and friction against the seabed and against continental shelves drags the bulge slightly ahead of the line joining the two bodies. That displaced mass exerts a small forward pull on the Moon, feeding it angular momentum and lifting it into a wider orbit, while the Moon's answering pull acts as a brake on Earth's spin. Nothing is created in the exchange. Rotational energy of the planet is converted into orbital energy of its companion and into heat dissipated in shallow seas. Slower rotation means a longer day, and the lengthening amounts to a couple of milliseconds per century, small enough that only the accumulation of many centuries makes it visible. Records of eclipses kept in Babylon, China, the Arab world, and medieval Europe give the demonstration. When the timing of an ancient eclipse is calculated on the assumption of a constant rotation rate, the predicted path of totality falls thousands of kilometers from where the observers said they stood, and the discrepancy grows steadily the further back the record lies, in the manner expected from a clock that has been running down. Fossil evidence points the same way. Growth bands in Devonian corals, laid down some 380 million years ago, have been counted to suggest a year of roughly 400 days, each of them correspondingly shorter, and layered tidal sediments from far earlier periods preserve rhythms that can be read as monthly and yearly cycles under a faster turning Earth. Running the present rate backwards, however, produces an impossibility, placing the Moon at Earth's surface something like 1.5 billion years ago, long after the samples say it formed. The resolution is that the rate has not been constant. Tidal dissipation depends strongly on the shape and depth of the ocean basins, and the present arrangement of continents happens to bring the ocean close to resonance with the tidal period, making the current epoch one of unusually strong braking. Through much of the past, with the land assembled differently, the coupling was weaker and the recession slower, which is why geological measurements of ancient day lengths are valued as constraints on a history that theory alone cannot supply. Extending the process forward gives a picture that unfolds without drama. The month grows longer as the orbit widens, the day grows longer as the spin decays, and the two periods creep toward each other across tens of billions of years, toward a state in which Earth would keep one face turned to the Moon as the Moon already keeps one face turned to Earth. Long before that, the widening orbit will have shrunk the Moon's apparent size below that of the Sun, and total solar eclipses, which depend on the near coincidence of the two disks in the present era, will cease to occur, leaving only the annular kind. The Sun's own evolution will intervene before the double synchrony is reached. so the endpoint remains a calculation rather than a forecast. While the measurement continues, night after clear night, impulses of light returned from 3 sites where machines were set down and left running. We are going to stop here. The music will carry on for a while, and then it will fade on its own. There is nothing more to do tonight. Rest well, and see you very soon.